Hi everyone, welcome to the final week of the organic chemistry seminar. Yay! Almost have a break except I've started 2 more. So this will be the last recording. I'm going to upload about 1 trillion videos tonight to finish off the seminar series. And hopefully you guys can use it as a reference tool or an exam to study to them. This is kind of the pinnacle of everything. So how do we create one compound, organic compound, from another? And we do that by swapping the functional groups. I'll share my screen so you can see it. So we have combustion reactions. Where we have the complete combustion of an alkane. We have substitution reactions, addition reactions. Then we also have we know and we remember the chemical properties are all to do intermolecular forces. Hopefully by now you've listened to me harp on about these long enough. That you know this. Any question in organic chemistry can be answered with intermolecular forces or some other way of saying that. A few of my year 12 students have just decided that's the answer for everything in chemistry. I think they finally lost their minds like that. So the polarity, the location of double bonds, and the location of free electron pairs. So the polarity or the lack thereof is the dispersion forces. Location of the double bonds is dipole-dipole forces. And the location of the free electron pairs is hydrogen bonding. So we have the alkanes, haloalkanes, and alkenes undergo chemical changes via reaction. And we can produce new hydrocarbons from that. What relevance that has to the real world, I don't think there is any, but we're going to learn about it anyway. So substitution reactions, shock horror, we substitute the functional group. So instead of there being a hydrogen, we swap it out for a hydroxide. Addition reactions, where we get rid of the double bond. Elimination reactions, we produce a double bond. Combustion, so combustion, we're talking about alkanes, so let's use methane. So CH4 is methane plus O2 produces water, CO2, and heat. So in a combustion reaction, there is none of the original reactants left, and we produce 2 new reactants and heat, or the 2 new reactants will almost certainly be water, carbon dioxide, and energy, which is in the form of heat. You can hear my mad toddler making himself known. So combustion of alkanes. This is a Bunsen burner, and you can see down there the reaction that I just drew. Methane plus oxygen produces water, carbon dioxide, and energy. This is the basis of fossil fuels. So the CO2 that's produced by burning it is part of the reason why we have climate change. People get upset when you say global warming now. So, tattoo this backwards on your forehead and look in the mirror. Remember, by that I mean remember it. There's 11 different reactions. We can produce all of the different compounds except for amide, carboxylic acid. The rest we can produce from a hydrocarbon. So again, I would screen snip that You can't see me pointing the screen, but I would screen snap that. So, first reaction is an alkane to a halo alkane. So if we use ethane as an example, and the halogens are in group 7, remember? So let's look at, use chlorine for an example. What happens here is the hydrogen here is replaced by the chlorine here. Just gonna shut the door. So this is what's called a halo alkane. So we're replacing the hydrogen with a halogen. And it has to happen in the presence of UV light. Now, UV light's important because it breaks that bond. The hydrogen flies off and the chlorine sticks on. That's the technical explanation. So you can see that here, methane plus chlorine, or Cl2, so plus UV light creates UV light is an important initiator in organic reactions because it breaks the bonds. It provides the energy and it also creates hydrochloric acid. Now, this creates methane and this is called chloromethane. Sorry, I should drink the water. So if I react ethane in the presence of iodine, fluorine. Don't know why that's Fi, it's just F, so my bad. In the presence of UV light, we would get the same thing, except instead of, we would get hydrogen, and then we would have F here, and we'd also get a byproduct of HF. So we can now we can go from methane, chloromethane, so which is our and then we add more chlorine. In the presence of UV light, we end up with what's called, as you can see there, a dihaloalkane. So we add another halogen onto our haloalkane and it becomes a dihaloalkane. So now we're looking at haloalkanes and what else they can produce. So a haloalkane, through a substitution reaction, can form a nitrile, an amine, or an alcohol. And we'll go through each of these then. So haloalkane to a nitrile. Nitrile is a functional group of NH2. Sorry, carbon to nitrogen, NH2. That's amine. So nitrile, so if we take our ethane molecule, so if we add, for some reason we think, hey, let's add cyanide. That's toxic, one of the most toxic things in the world. And then we add cyanide. Now if remember, a nitrile is carbon triple bond to nitrogen. We end up with that. So this forms a nitrile because we have the carbon backbone, the C end has broken apart and reattached itself onto the backbone, and our iodine, which is on here, this is a haloalkane, is now the other product. So substitution reaction where we substitute iodine for the nitrile group takes it from a haloalkane to the nitrile. Now there are quite a few reactions to go through. I'll send out all this. So, haloalkane to an amine. So an amine haloalkane to amine. So amine group is NH2. So if I add ammonia to anything, little hack, we end up with so we have ethane again. Chlorine is the example they've used here. We add NH3, which is ammonia. We end up with and the hydrogen all the way around. And then because we have one hydrogen left, and then we also have a floating chlorine, it produces HCl as well. So it produces the amine and also produces hydrogen chloride or hydrochloric acid. So we can also do the same thing and produce an alcohol. So the thing to remember these is they are substitution reactions where we're substituting the functional group with alcohol. So we know our haloalkane, hopefully I've said that enough times now. Same one as before. So bromine this time. So we add hydroxide in the form of sodium hydroxide. So in the form of sodium hydroxide. When we put them into a solution, Na and OH break off from each other, and the OH of the hydroxide replaces the and on the end we have OH. We know it's an alcohol because it has that hydroxide group. So the hydroxide has substituted the halogen group. Happens at room temperature. Now some of these reactions coming up do not occur at room temperature. Now we have the addition reaction. So we take an alkene, we make an alkane. So remember what's an alkene? It has the double bond between hydrogen and carbon. I mean, between the two carbon atoms, not between hydrogen and carbon. If the bond is broken, then the carbon atom is free to bond with something else. So we take an alkene to a dihaloalkane. So that's the alkane that has two halogen groups attached. So we go from alkene, di. So what we're doing here is we're getting rid of the double bond. So we would have so we add bromine again. What's going to happen? This breaks the bond here. So we end up with and then we would have two bromine attached. And we would also have H, no, we wouldn't have H2. So that's when we break down, we add two halogens to an alkene, we end up with a dihaloalkane. Again, all the questions that are on here are the final questions for this topic. So I'll send them to you by email. So now we can go from an alkene to an alcohol. So we react methane or ethane we take water at 300 degrees. We add hydrogen phosphate. Sorry, H3, not 4. H3PO4 or hydrogen phosphate. And we get the oxygen from water is liberated by the heat, and the catalyst and attaches itself to one of the hydrogen. again, the question afterwards is going to be the final question. Part of the final questions for the whole seminar. So the alkene, I'll probably I'll put on my list to a video of all the questions in there. So now we can go from an alkene. So again, we'll use ethane. Then we add a hydrogen halide, so hydrochloric acid, which breaks this double bond and creates the hydrogen and the chlorine molecule from here attach on here because we've broken the double bond. That's because there's a free bonding pair of electrons, and the hydrogen and the chlorine both need one, and they'll take the positions underneath the cuff. So this is, if you're doing your senior exams, this is something that we're going to focus on. So we have the poly. So we take an alkene to a polyalkane. So polymers are going to feature extensively in your exam. Poly is many. Mono equals one. Poly is many, mono is one. We take ethene monomers. So and this creates a polyalkane. So the carbon atoms, double bond breaks, and we get a chain of, so it just becomes an alkane, single bonds all the way around. And just it goes from monomers to a long single chain of alkanes or saturated hydrocarbons. So you'll know polystyrene, polyethylene. So poly equals many. So this polyalkane is made up of many alkene monomers. Wouldn't worry too much. So our final two reactions, probably the hardest ones to remember, but we will go through. So reaction 5 is a reduction reaction from an alkene to an alkane. Reduction 9 is an elimination reaction from a haloalkane to an alkene. The elimination reaction is reforming the double bond. So we have a haloalkane. Alkene. So we take a haloalkane and we add sodium hydroxide, so a strong base. You'll notice that we use heat, acids, bases, and catalysts in order to break bonds and reform them, because we need some kind of energy or something to break the bonds physically. So we add sodium hydroxide in the presence of heat. So the chlorine molecule comes off, reacts with the sodium to produce NaCl, or sodium chloride. The OH reacts with the hydrogen to become H2O. So we end up with so we've now reduced it back to the double bond. So we add the chlorine molecule, breaks off because of the heat and the strong base, reacts with the sodium chloride, with the sodium and becomes salt. The hydrogen that's liberated reacts with OH to produce H2O, and then all of a sudden we're back to the alkene. The last one is an alkene to an alkane, and it's probably the simplest. Alkene to alkane. We go and we add H2. This does nothing until we add a catalyst of some description, which makes the reaction happen. So what happens is the double bond breaks and the hydrogen atoms rearrange themselves, and we add 2 more H2. So it would be so now we're back to ethane. So ethene or ethylene, we add H2 and it becomes ethane again. So again, another thing to glue to your forehead, so every time you look in the mirror, you can see it. This shows all of the reaction pathways. So all of the steps required to produce one class from another. And you can tell by what's being added. So if I add cyanide, which is CN, it's going to produce a nitrile because that's a carbon to nitrogen bond in the functional group. If I add ammonia, it's going to make propylamine because it's got amine on the end of it, so it's got NH2. If I add hydroxide to something, or sodium hydroxide to something, it's going to produce an alcohol. If I add water to something, probably going to become an alcohol as well. If I add a halogen to something, it's either going to become a haloalkane or a dihaloalkane. And if you can snip this, I'll send you the work. I'll send you this the word presentation, and you can answer the question. So I just want to say thank you to everyone, although it doesn't seem to be anybody watching this on YouTube, so I'm not talking to myself. I'll hopefully see most of you in the assignment and exam prep seminars that we're doing now. Thank you.